All right, we're taking a look at question 16.6, and before we took a break, we looked at the molecule and we said, well, we've got a fully conjugated system, and so I could either add a proton at the carbon that I have highlighted in yellow or the carbon that I have highlighted in green, and I'm going to end up with an allylic carbocation like this. So I'm going to redraw this curved arrow that I have on the top just to give myself a little bit more space. So I add the proton to the carbon that I had highlighted in yellow. And let's draw that carbocation again. Of course, it's an allylic carbocation, so we end up with this, their double bond, and there we have it. Now, of course, we can draw a resonance contributor for this. So let's draw our resonance arrow that shows the delocalization of the electrons, and we end up with the second resonance contributor, which again is another allylic carbocation here. And now, to give the products, all we have to do is draw the nucleophilic attack occurring in either of these carbocations. So we're going to draw our bromide. I'm not going to put in all the lone pairs. So there's the bromide, and the bromide is going to attack the carbocation. So it's going to go here and here. Let's draw the products. So we end up with this product, this, and of course this is racemic because this is a stereocenter. The bromide can attack from either face of the molecule. What am I doing here? Oh, I put my positive charge in the wrong place here, didn't I? I should have put my carbocation there. There we go. That's a lot better. No, it's going to attack here. Instead of vinylic carbocation, that's not right. That's completely wrong. So we end up with this. And of course, this is racemic as well because this is a stereocenter. We'll put racemic there. Thanks, Sandrina. Yeah. So I had the positive charge in the wrong spot. So now we're going to do the same thing, but we're going to add the proton from the acid to the carbon in that I had highlighted in green. So look, I'm just going to copy and paste this just to show you it's the same thing. So copy, I'll paste this guy right here, and it's somewhere, oops. There we go. So I'll just delete these curved arrows. I'll delete the yellow highlighter, and I'll highlight this carbon in green. So now I'm going to do the proton being added to the carbon in green to produce a vinylic carbocation. Let's draw that vinylic carbocation, which is going to look like this. And now we can also draw a resonance contributor for it, where we show the delocalization of the electrons. And we get a second allylic carbocation. So we have our double bond here. We have the positive charge up here. And those are the two resonance contributors. Now I'm going to draw the nucleophilic attack by the bromide on each one of these allylic carbocations. I'm going to delete my resonance arrow. So I end up with a nucleophilic attack here or here. And let's draw the products. So I have this product. I have the bromine over here. And of course, this is racemic because it can attack from either face of the molecule. And for this one, we end up with a racemic mixture as well because we end up with the stereocenter. So we end up with a total of 4 racemic compounds. I'll use my green pen here. We end up with 1, 2, 3, 4 different compounds. Again, this question doesn't have anything to do with kinetics and thermodynamics. It's just asking us to identify all the different products that we can form. Are there any questions about that one? So again, this is question 16.6c. And yes, there are a lot of products that you form here. However, we just follow a stepwise approach. We add hydrogen, to the double bond. We're not worried about Markov-Nikov. We just want to make an allylic carbocation. Once you make the allylic carbocation, we draw the other resonance contributor, and the nucleophile can attack either carbon with a positive charge, either carbocation. And if you have an unsymmetrical molecule like we do here, well, that means you're going to have to draw two different allylic carbocations after the addition of the proton. Give me a thumbs up if you follow me on that, even if you're with me 50% of the way, because that is not an easy problem. Are these two sets diastereomers? They're not diastereomers, no, because there's no, if you look at this molecule, there's no other chiral center in here. There's no other chiral center in here. There's no other chiral center in here, and there's no other chiral center in here. All right, yep, good enough. There we go. Again, not an easy problem, but if you follow the stepwise approach, you'll definitely get all the products. So I recommend giving these, some serious practice before stepping into the quiz. Well, let's move on and talk a little bit about pericyclic reactions. So let me go back to my slides here. And we've covered the first few sections of the chapter. Now we're into something that's kind of a departure from a lot of what we talked about in Organic Chemistry 1 and Organic Chemistry 2. Because now, if you think about everything that we've done up to this point, every reaction that we looked at either involved an ionic mechanism, like an SN1 or an SN2, or an E1 or an E2, or a radical mechanism. And we saw that in, chapter 10, for example, and a little bit when we talked about formation of peroxides. But pericyclic reactions, which we're going to look at in sections 16.6 and 16.7, have nothing to do with ions or free radicals. So kind of interesting. There's three types of pericyclic reactions. The one that we're mostly interested in this class are cycloaddition reactions. Under the umbrella of cycloadditions, you find a reaction called the Diels-Alder reaction. It is what we're going to focus on in section 16.7. But a Diels-Alder, again, is a type of cycloaddition reaction. And you can see that the mechanism for this reaction is concerted. What does concerted mean? It means that all of the curved arrows happen at once, all drawn simultaneously. And check out what's happening here. You notice that you're breaking two pi bonds. You're breaking a pi bond here. You're breaking a pi bond here. And you're forming two sigma bonds. Check it out. Sorry, did I say two pi bonds? Yeah, you're breaking a total of two pi bonds, I guess, and you're forming two sigma bonds here. And yeah, you're actually forming a pi bond over here as well. Anyhow, I'll summarize that in a little bit. That's neither here nor there at the moment. But you end up losing two pi bonds. And yeah, out of three pi bonds, you lose two, I guess is what I'm looking at. And then you end up with one only in the end. And of course, you form two sigma bonds in the process. Anyhow, that's a lot of mumbo jumbo, but I have that summarized in a little bit. Electrocyclic reactions, we're not really going to look at these at all. They're covered in this chapter, but we're not going to study them. And then we have something called a sigmatropic rearrangement, and we're not going to be looking at these either. We're going to be sticking to cycloadditions. However, all three of these types of pericyclic reactions have four characteristics in common. In all of them, you have a concerted mechanism. That means that all curved arrows are simultaneous. The mechanism involves a ring of electrons, and you saw that in all three of those. The transition state is cyclic, and the polarity of the solvent generally has no effect on the reaction rate since the transition state doesn't have any charge. It's not ionic. Well, what I was trying to get at when I was talking about cycloaddition reactions is that you end up gaining two sigma bonds, but you lose two pi bonds, okay? Whereas in an electrocyclic reaction, you gain a sigma bond and you lose a pi bond, and then in a sigmatropic rearrangement, you get no change in the number of sigma or pi bonds. But again, what we're going to focus on in this chapter is going to be the cycloaddition reactions, where you gain 2 sigma bonds and you lose 2 pi bonds. Well, let's move on and let's just do a brief introduction to Diels-Alder chemistry. Diels-Alder reactions, very, very useful. Why? Because you make new carbon-carbon bonds. More than one. Check it out. You end up making a carbon-carbon bond in both of these bonds that I have highlighted in yellow. We also refer to Diels-Alder reactions as 4+2 cycloadditions because the species that has 2 double bonds, we call that the diene. It has a total of 3 atoms that are involved in the transition state. And the alkene that we call sometimes a dienophile has 2 atoms that are involved in the transition state. And of course, you've got to be able to draw the curved arrows for a Diels-Alder reaction like this. Again, you saw that the mechanism is concerted. You can draw it clockwise. However, I can delete all those arrows and you can draw it counterclockwise. You're going to get the exact same thing. It doesn't matter if you draw the arrows clockwise or counterclockwise. Either way, you're going to get the same product. Let's take a look at the potential energy diagram for this reaction. We start out with our diene. So this is our diene here. This alkene, we call this the dienophile. The diene and the dienophile react together. We form our intermediate, which is higher energy, or transition state, and then we form our product. Notice that our product is more stable than the reactants. Why would that be? Well, you see that we gained 2 sigma bonds, and we know that sigma bonds are stronger than pi bonds. Pi bonds are weaker. So it makes total sense that your product is going to be more stable. Check it out. It says that most Diels-Alder reactions are thermodynamically favored at low to moderate temperatures. Why? Because product stability is going to dominate. However, once you get to temperatures above 200 degrees Celsius, then what's going to predominate is what's called the retro Diels-Alder. So check this out. Just stop with me for a second and look at this. It's really neat. If you do the reaction at a temperature less than 200 degrees Celsius, you form the Diels-Alder product, everything is great. If you do the reaction at a temperature usually greater than 200 degrees Celsius, and this is approximate, even if you were to form some of the product, it just goes right back to giving you the starting materials again. So you got to be very careful with the temperature because you end up breaking this apart and just reforming the diene. Well, why the heck would that be? Why? I thought that, you think of chemistry, well, if you turn up the heat, shouldn't it just make the reaction occur faster and faster? That's what, they taught me in general chemistry. And I even told you in in organic chemistry 1 that usually if you increase the temperature of a reaction by 10 degrees, it doubles the reaction rate. Well, obviously it's not true here. And the reason why can be explained according to our good friend, Dr. Gibbs, Willard Gibbs, and Gibbs free energy. So this goes back to general chemistry 1 and 2 and organic chemistry 1. And we said that when delta G is negative, the reaction is spontaneous. And when delta G is positive, the reaction is non-spontaneous. Well, what's the formula for delta G? Delta G is equal to delta H minus T delta S. Well, what's our delta H? Remember that when we calculated delta H way back in chapter 6, we said that delta H was equal to the H of the bonds broken minus the H of the bonds formed. Okay, that's how we calculated it. We used bond dissociation energies, is what we actually use. So I'll just replace this with BDE for bond dissociation energy, bond dissociation energy. Well, if you're breaking pi bonds here, you're breaking 3 pi bonds, and here you're forming 1 pi bond and 2 sigma bonds. A sigma bond, sigma is stronger. Your sigma is stronger than pi. Therefore, if you're breaking 3 pi bonds, you're going to be taking a smaller number. And then if you're forming bonds that are stronger, then you're going to be subtracting a large number. And therefore, you're going to get a negative number. So that means that your enthalpy term is going to be negative. There's nothing you can do about that. So delta H is always negative. So what about the T delta S term? Is that negative or positive? Well, let's take a look at it. If you're taking 2 reactants, the diene and the dienophile, and you're combining them together to make a single product, well, what's happening in terms of entropy? Your entropy is decreasing. Entropy is going down, right? Because you're making something that's more organized. Therefore, delta S should be a negative number. So we'll put here that this is negative, and then your delta S term is negative. So if we take a negative delta S and we subtract, or we multiply it by a negative delta T, negative times a negative gives you that this whole entropy term must be positive. Well, if you take a negative and subtract a positive number from it, what do you get? Do you get a negative number or a positive number? It depends. If you take negative 2 and you add, a small term positive number, like let's say you take negative 2 and you add positive 1, what do you get? You get negative 1. But if you take negative 2 and you add, getting ahead of myself, you take negative 2 and you add positive 3, then you end up with plus 1. So that means that you can control whether delta G is positive or negative, right? You can control whether the delta G outcome is positive or negative by doing what? You can adjust the temperature. If the temperature is high, right, if the T is a big number because temperature is in Kelvin, and Kelvin is always positive, if you jack up the temperature really high, what's that going to do? It's going to make the temperature, or the entropy term, a giant number. So at high T, you're going to end up with a positive delta G, but at low T, then the entropy term is a lower number, so you're going to end up with a negative delta G. And that's the answer right there. So for a Diels-Alder reaction, the enthalpy term has to be larger than the entropy term in order for the reaction to be favored. How do you make the entropy term lower? Well, you do it at a lower temperature, something that's lower than 200 degrees Celsius. If you jack it up to a super high temperature, the retro Diels-Alder is going to be favored. Why? Because the delta G will be positive. Give me a thumbs up if you follow me on that. So Nick asked me, does a Diels-Alder reaction always form a cyclic compound? The answer is yes. You always end up forming a cyclic compound when you do a Diels-Alder reaction. Well, let's just review a couple more terms here. I already explained to you what a diene and a dienophile was. And in order for this reaction to work well, you probably noticed this little X here, and you're like, well, what's the X? It says that in order for the dienophile to be reactive, it has to possess some kind of electron withdrawing group. Sometimes we call that an EWG, in order for the reaction to proceed. It says if it doesn't have an electron withdrawing group, it requires such high temperature that it doesn't favor product formation. So if you're wondering, like, what are the electron withdrawing groups that we could add, Mr. Dion? Well, let's take a look. It says here a good electron withdrawing group is a carbonyl. When an electron withdrawing group is attached to the dienophile, then the reaction is going to be spontaneous. Right? We know that this is electron withdrawing, this carbonyl, if we just think about resonance, and I'll just draw it for one of these. If you draw the resonance structure here, you end up with something that looks like this, where we have the negative charge over here, our group over here, and we have a positive charge over here. So you can clearly see that the carbonyl is electron withdrawing. There's a dipole going this way. All right, and when we have that electron withdrawing group, the reaction is going to be spontaneous. We could have either a ketone, we could have an aldehyde, we could have an ester, we could have a carboxylic acid, we could have a nitrile, and all of them serve as electron withdrawing groups. And with that, we're going to call it a day. And then when we come back on Friday, we're going to finish up this section. We're going to look at the stereospecificity of Diels-Alder reactions. We're going to practice drawing the products of Diels-Alder reactions. Then we're going to talk about the conformation of the diene. We're going to talk about what's called the Endo Rule. So I'll teach you all about the Endo Rule, which is covered here. So the Endo Rule is pretty quick. Then we're going to talk about Diels-Alder regioselectivity. And that is the very last thing that we cover in this chapter is Diels-Alder regioselectivity. So just keep in mind, 16.8 through the end of the chapter, we do not cover it in Chemistry 3111.